Professor.
Yep. What's up?
So on the exam, obviously we're like going to be doing it by hand. And I'm assuming you're not going to want us to write the whole code. So what would be like the main pieces that or should you understand the whole code in order to kind of grasp the exam?
Yeah. So I did some thinking about it over the weekend. I think what I'm going to do for the exam, it'll be kind of half half. And so for the 1D methods, all the ones that we kind of finished going over, I think those ones you'll be able to execute by hand, at least maybe one or two iterations of those algorithms.
Okay.
Um, for the multi-dimensional methods, those ones are kind of impossible to do by hand. And so I think what I'll do is that I'll have you write what's called pseudocode. So pseudocode is not MATLAB code exactly, but it should get the same kind of logic, the same kind of you know idea across. For this week, we're going to do some examples of that, of kind of what pseudocode looks like and what I would kind of expect for the exam. Yeah, so we'll start doing that this week and next week.
Cool. Thank you.
Yep. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Election day. It's, a lot of things are probably going to change after today. Hopefully for the better, but probably, probably like most people, I think, a lot of us are kind of just holding our breath. Just because, depending on who becomes president, I think a lot of things are probably going to change. So, here's hoping our country will be okay after today, after this week. Okay, all right, so the plan for today is we're just going to continue on with our lecture notes. So last Thursday, we started talking about multi-dimensional methods for nonlinear programming. So we went over our first algorithm, which is Monte Carlo. So that is kind of a really nice method to go over. Good one to start with, I should say. It's kind of the first one everyone learns. It seems really silly and really dumb, but it actually works. So today we're going to build on that, and so we're going to be talking about our next two methods. The first one called random walk, and the second one called coordinate search. Okay. Okay. Announcements. So homework 4 you guys turned in end of last week. So homework 5 was just posted this afternoon. So homework 5, you guys have about a little bit less than 2 weeks to do it. So it is due on Sunday, November 17th. So that's not this Sunday, but the following Sunday. The majority of the problems on this homework are going to be MATLAB implementation problems. So there's going to be a short answer question that you have to answer first, but everything else is going to require a code, right? I'm not providing you any starter code for this homework, but all the problems can be done, basically with very minor modifications to the example code. And so, if I did provide you guys starter codes, they would just basically be the exact same thing in the example code. So, we're going over these example codes in class, so just kind of make sure that you're going over them yourself. Because it's one thing to kind of listen to me talk about kind of the logic of the code, but it's another thing for you to kind of try it yourself and go through the code yourself and really kind of understand how the algorithm is actually implemented in the code. Okay. And so, when I leave kind of notes in the lecture notes here to, check this code, actually go in and check, because, it's one thing to learn about how the algorithm works. It's another thing to try to implement it in code yourself, right? And so that's probably the most important thing from this section. Okay. Other announcement I want to make is that the date for the next midterm is pretty much set, and so it's going to be the last Thursday before we leave for Thanksgiving. So I realize, that week's probably gonna be really busy for you guys, and so, I apologize for adding kind of one extra thing on top of that week. But just with the timing and everything, just, making sure we get through, making sure we just have enough time to get through all the nonlinear programming stuff. That's kind of the only date that I could have. So I think the exact date for that will be Thursday, November 22nd. So it's the Thursday after this homework's due. And it's going to be based on homework 4 and homework 5. So that's not 1D nonlinear programming problems and multi-dimensional nonlinear programming problems. Okay. So I got a question before class started today about how I expect to kind of test you guys on this stuff, because a lot of it has to do with the MATLAB. So for the exam, I did think about it over the weekend. I think what I'm going to have you guys do on the exam is to write basically pseudocode in terms of how these methods are implemented. Okay. And so if you've never seen pseudocode before, pseudocode is basically just you basically write line by line in terms of what your code should be doing without having to worry about the exact syntax of MATLAB. Okay. So it's basically explaining kind of the logic of your code without having to actually code, right? And so, if you've never done that before, if you've never seen that before, all the examples that we're going to do in class this week and next week, I'll show you, what a pseudocode looks like, just so you kind of know what to expect for the exam. Okay. All right. Any questions on any of that before we get started for today? Okay. All right. So let's go ahead and get started with our next algorithm. Okay. So, this whole unit, I think we'll be working on this whole unit this weekend and next week. I think it's going to take 4 full lectures for this. We're doing multi-dimensional nonlinear programming algorithms. Okay. Okay. And so it's a very, very fancy title, very, very fancy name. But we can kind of break this down and kind of figure out what it means, right? So the multidimensional part, pretty straightforward. All that really means is that we're working on optimization problems with multiple design variables. Okay. So everything we did the last couple of weeks have just been one-dimensional methods. Now we're doing multidimensional. Okay. And this is kind of where the bread and butter of where optimization really comes into play. Because most of the times, if you have just a one-dimensional problem, most times you don't really need optimization for that. You can kind of find out the optimal value just from your own. But it's when you have complex engineering systems with multiple variables, 5, 6, 7, 8 variables that all kind of depend on each other, that all affect the system in complex ways. That's when you need an algorithm to help you choose those parameters. Okay. So everything that we're going over for, and that includes last Thursday too. So Monte Carlo as well. Everything that we're going over this week and next week, I would consider to be kind of the, modern, all of these are very modern methods that are used and practiced all the time. Okay. And the nonlinear programming part of this, all that really means that we're writing algorithms that don't depend on the objective function derivatives. Okay. So that's all that means. And so the next algorithm that we're going to go over, it's kind of like the cousin of Monte Carlo, but it actually behaves quite differently. As an algorithm called random walk. Okay, I've had some colleagues call this method the drunken walk algorithm. You know, optimization people are really funny. They give their algorithms really funny names sometimes, and it helps make them really memorable. Okay, so how does random walk work? Well, let's to kind of start random walk. It's really actually interesting to compare this to Monte Carlo, right? And so let's kind of remind ourselves just very quickly how Monte Carlo methods work. Okay. Okay, so the Monte Carlo method, if you recall from last Thursday, basically it just chose a random value for each of your variables on each iteration of the algorithm. Okay. Okay. And so in a sense, you can say that each point or each new location doesn't really depend on the last one because you're kind of just shuffling everything up entirely. Okay. And so what this ends up looking like, if you were to kind of visualize and see what a Monte Carlo method looks like, it kind of almost looks like you're just kind of jumping around all the time. Okay. I think another nice analogy or another really interesting analogy for Monte Carlo is that it almost looks like you're just kind of randomly throwing darts at a board. Okay. And so it looks like this, right? And so we have a typical design space here. So this is a two-dimensional problem. So we have design variables x1, x2, right? If you were to kind of visualize how the Monte Carlo method works, it would look like you're just kind of drawing a bunch of just random x's around the domain, okay? For each x there is a random guess for the for the design variables. Okay. And so what we said last time is that, even though this seems very haphazard, eventually you're going to converge on the solution just because, eventually just by the law of large numbers, you're going to get a guess that's very close to the optimum, right? So maybe you take a guess right here, okay? And that just ends up being pretty close. And so you end up with an optimal solution from that, okay? Now, the Monte Carlo method has one very big weakness, and its weakness is actually its greatest strength as well, right? And so the strength of the Monte Carlo method is that, it really has no memory of kind of where it was before. So it just kind of hops everywhere. And so if it finds something bad, it doesn't matter. It just kind of hops away, okay? But what's bad about that is that if you are hopping around with Monte Carlo and you find something that's pretty good, right? So let's say that you end up right here, right? Which may not be at the optimum, but it might be pretty close, right? Monte Carlo has no way to actually remember that. And so Monte Carlo will say, all right, that's cool. Let me hop somewhere else. Right? And then from here, it's like, oh, that was bad. Let's hop somewhere else. Right? Sometimes you kind of want to stay in a particular neighborhood if you feel like you're getting close. Okay? And so there's no way to kind of stick around a particular region. Eventually, if you take enough random guesses, you'll end up back in that region for a guess or two. But it's kind of feels like a lot of wasted effort because maybe you find a pretty good spot, but then you hop away from it, and then you have to wait for a bunch of other random guesses before you come back. Okay, and so in that sense, Monte Carlo, you know, can be quite inefficient because it takes you a while to find kind of a sweet spot if you're designed them. Okay. So the idea of random walk is to kind of keep within the same spirit of using randomness to kind of help you converge, but it kind of gets around this problem by avoiding this problem of jumping away from a good spot. Okay. And so the way random walk works is that random walk, instead of jumping around really randomly around the domain, random walk is really like, it kind of simulates yourself kind of walking around in a room, right? And so where you step next kind of depends on where you are currently. So the idea with random walk is to, take random steps, in a random direction from your current location. Okay. Let me just go ahead and visualize that again for you. Okay. Okay. So once again, I've drawn our design space here, X1, X2. And so let's say that we start our random walk, right here. Okay. We're going to start here. Okay. So if this were Monte Carlo, it doesn't really matter where we start at all. We would just kind of jump randomly within the domain. Okay. But if it's a random walk, what we can say is that, all right, we're starting here. Let's try taking one step in this direction right here. Okay. So the next data point or the next iteration that we check is going to be within the same ballpark, within the same region as our starting. Okay. And so the idea is to kind of stay within the same region where, maybe you're starting from a good region. Maybe you have some kind of prior knowledge of your engineering design system where you know where the optimal values should be approximately, but you just want to kind of fine tune it a little bit. Okay. So random walk basically allows you to do. Okay. But at this point, random walk will check. And so, it's not just going to keep stepping randomly. You have to kind of step with purpose as well. And so after you take the step in a random direction, the next step is to basically check, right? We want to check and see if taking this step led to an improvement of our objective function. Because ultimately that's what we want, right? We want to improve our objective. We don't just want to just step randomly just for the sake of step, right? And so if this led to an improvement over the objective function, that's great. And so we actually, step here, and this is our new kind of current location. So if yes, stay here. Okay. But if it doesn't lead to an improvement of the objective function, then you just go back to the previous one, right?
Stay there. There's a possibility of
Yeah, so this isn't the end of the algorithm. So you're basically going to keep repeating steps. But basically, you're trying to see if the new location is an improvement of the old. And so when I say stay here,
so you're saying now you're using this again.
exactly. So then now you're using this as kind of your base. And so now you're going to take a random step around here. Yeah. Yeah, so it kind of is like drunk walking. So if you've ever walked around drunk in your apartment, sometimes the way that you kind of navigate is that you take a step and it's like, is that a wall? Ow, and you hit it and then you go back. But if it's not a wall, then you keep moving forward, right? And the goal is to get to the bathroom so you don't yak all over your carpet. And then, because you're drunk, you're kind of just taking steps in random direction, hoping that you get there. Yelling at your roommate to help you, like he's just laughing and filming you at the same time. All right, and so the idea is, you're just going to repeat this over and over again. So you're going to take a step in a random direction, see if it helps. If it doesn't, go back. If it does, you stay there, you take another step, okay? And eventually, you're going to keep taking random steps. Okay. Eventually, the idea here is that, if you keep taking steps with this kind of logic, you're going to end up at the optimum of the design space. Okay. Any questions on that? Okay, cool. All right, so so how does this work? What's the mathematics? So we have a stepping formula here. So I should say maybe this is the formula. All right, so the formula for determining the next step of random walk. Right? All right, so it's quite simple formula. So we have xi plus 1. Okay. So xi plus 1, this is going to be our next trial location. So the next step in our random walk. Okay. This is equal to xi, where xi is our current location. plus. We have lambda. So lambda here is the step length, right? So, we have to determine how far we want to step in a certain direction. Okay. And we're going to multiply by di, where di here, this is our random direction. Yeah.
So the step length is going to be constant.
Yeah. No, it's not actually. So it's going to change. Yeah. So kind of the idea with the step length is that, after you've taken a few steps, generally the logic is that you're getting closer to the optimum. And so your step length should be being reduced at that point. So the idea is that first you take big steps because you don't really know where you are. And then once you start to kind of hone in on the optimum, you take small steps. Okay. So we're going to be using that formula. I'll talk a bit more about how to determine DI. So DI is kind of the whole kind of linchpin to this whole this whole operation here. And how we determine that is going to be kind of we're going to use random number generators within our code as well. Okay. All right. So let's go over the algorithm. Okay. So random walk, because our successive guesses depend on our current location, we need some kind of initial guess. Right? So in that sense, it's not that different from our 1D methods. Okay. So our initial guess, we'll call it x naught vector. Okay. Right. So how you determine that initial guess, there's lots of different lots of different logics for that. Sometimes if you already kind of have some intimate knowledge of your engineering system, you probably can get a good guess for that initial guess. Another way to kind of determine that initial guess is if you have the upper and lower bounds for each of your design variables, you can just kind of start right in the middle. That's usually not a bad idea too. Okay. Or another really interesting way to get that initial guess is, maybe you run the random walk after you run the Monte Carlo. So maybe you run Monte Carlo first, and so Monte Carlo kind of jumps around kind of randomly. And then you pick out the best guess from Monte Carlo and use that as your initial guess for random walk. Okay. So that's kind of a strategy of kind of combining different algorithms together. We're going to talk more about that probably starting next week, right? Just kind of remember that for that. Okay. Another thing that you need to do in this first step here is you need to initialize some other variables. Okay. So there are other variables that we need to keep track of in our code in order for our algorithm to run. Okay. So just like I mentioned, generally speaking, when you run the random walk, you're going to keep decreasing the step size. And so one other variable that you're going to need to specify here is the minimum allowable step length. Okay. Another thing we need to initialize is the maximum number of iterations. Okay. So similar to Monte Carlo, you can keep a random walk going forever if you want. But you have to stop it at some point. You can't just let your computer just tire itself out. Okay. And then C, you also need to get your initial step length as well. Okay. So how big of a step are you going to take in that first iteration of the algorithm? You need to determine that as well. Okay. So step one is kind of all the initialization stuff. And so that's kind of takes place in the first few lines of your code. Okay. Step two. So step two in this algorithm is we need to evaluate our objective function at our initial point. Okay, so we'll call that F naught. Okay. So whatever the values of our objective function of our initial point are, we plug those into our objective function and get that point. Okay. All right. And so now that we have everything initialized, now we can start taking random steps. So step three here is to take a random step. Or I should say, take a step in a random direction. That's probably more accurate. Okay. Okay. So here's how to take a step in a random direction. Okay. So for each design variable that you have, okay, and so if you have a two-dimensional problem, you're going to sample two random variables. If you have a three-dimensional problem, you have three random variables. Okay. For each design variable, we're going to sample a random number. And the random number is going to be between -1 and 1. Okay. And so each of those random variables I'm going to call RJ. Okay. Where J there is the index for the design variable. Okay. Okay. So I'm going to put all of those random variables into a single vector. Okay. And so we're going to create a vector here. And I'm going to use a column vector just because it's kind of easiest to visualize. Okay. Where our vector here is all of our random variables. So in this case, we have n random variables. And so, we create a vector for them. Okay. All right. Next step is we need to normalize this random direction here. So we're going to compute the magnitude of this. Okay. And so we're going to use our distance formula here to compute the magnitude. So we have square root r1 squared plus r2 squared plus ... plus rn squared. Okay. Because we want to make sure that the random direction that we're stepping in is a vector of magnitude 1. Okay. Because we don't want our random direction here to be we want our step length to be determined purely by our step length. We already have a variable for that. So we don't want this random direction to kind of bias that either above or below that. Okay. Okay. So we're going to use the magnitude to normalize the vector. Okay. i.e. make its magnitude 1. Okay. And so after we normalize the vector, then this is going to be our random stepping direction di. So di is equal to 1 divided by the magnitude, r1 squared plus r2 squared plus dot 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 plus rn squared multiplied by r1, r2, dot dot dot, rn. Okay. Okay. All right, so now that we have our random direction, we can go ahead and take a step. And so we're going to use our stepping formula that we kind of wrote down before we launch into the algorithm here. Okay. So we have x I plus 1 is equal to xi. Okay. Oops. Xi plus 1 is equal to xi plus lambda, which is our current step length, multiplied by di. All right, so that's where most of this algorithm is here. So determining our random directions, taking a step in and taking a step in that direction. Okay. All right, so I was quite detailed with this part just because we're going to see this implemented in code in a second, so I want to make sure that you kind of understand the logic of it. Okay. Any questions on this? Okay. All right, step 4. Now that we've taken a step, we need to evaluate our objective function at that location. So that's pretty straightforward to do. We just plug in, whatever the value for all of our design variables after taking that step into our objective function. Okay. Step 5, we're going to see if taking the step led to an improvement of the objective function. And so if the objective function improves, okay. And so if the objective function improves after taking the step, we accept the new point as our current one, and then just kind of move on from there. If not, and so if it doesn't lead to an improvement of the objective function, then we reject it and we return back to our previous location before we took that random step. Okay. Step six. Step six is just to repeat steps 3 through 5, up to a certain point. Okay. So we're going to repeat steps 3 through 5 until we reach the maximum number of iterations. Remember, we specified that parameter early on. Okay. Okay. So at this point, let's kind of pause and kind of see. And so up until this point, we've been taking all these random steps, but we've been taking them all with the same step size. Okay. So step 7 here, the idea is that once you've kind of taken a few random steps, and honestly, probably the majority of the steps that you're going to take are probably going to be rejected, because there's usually kind of only one path that leads to the optimum. But the idea is that at this point, you've probably taken at least 5 or 6 steps to improve the objective function. Okay, so you're getting warmer, right? You may not be there exactly yet, but you're getting closer. Okay, and then as you're getting closer, you want to be a little bit more careful with your steps. So you want to reduce your step size so that you can kind of kind of fine tune your optimum. So step 7 here is to reduce the step size. Okay. So we should be getting close. Okay. And so since we should be getting close, we should be taking smaller steps to refine our search. Okay. Now, how quickly you reduce your step size is up to you. So you can be very aggressive and you can do something like you can reduce your step size by half, or you can be a little bit more careful and, maybe you reduce your step size only by about 20%, and then you just kind of go back from there. Questions?
So that max number of iterations we said at the start was for the first step size, or
Exactly.
for each step size.
For each step size.
Got it.
Yeah. So the idea here is that, you take a bunch of random steps with a certain step size, you repeat that for, maybe say 100 times, and then you reduce the step size and you do another 100 from it. Okay. And so after step 7 here, you're going to return to step 3. Okay. And then you're just going to do this kind of all over again. So you're going to take random steps, but this time with a smaller step size. Okay. Okay. And then 8 here, so you're just going to repeat this until the step size gets too small. So if you remember from the beginning, we defined another variable there for the minimum allowable step size. So you're just going to repeat this until that step size falls below that threshold. Okay. Because once your step size gets too small, then you're basically not really taking any steps at all. And so, it's kind of pointless to keep stepping. Okay. All right, so that's the algorithm. So, in concept, random walking is pretty straightforward. It's just that, there's kind of a lot of steps to kind of actually make this happen. All right, any questions before we jump into an example? Okay. All right, so for this next example, again, there's really no way for us to kind of work out a problem like this by hand. And so I'll show you kind of the problem that we're going to work on. I'll show you the code, and then I'll show you kind of what a pseudocode for that code would look like, just so that you can kind of see it and kind of prepare for it. Right? Okay, example. So let's say that we want to minimize. We want to minimize the following 2D objective functions. We have minimize f of x1, comma x2 is equal to x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay. And so we're going to optimize this function using random walk. And so we need a starting point. Okay. So we're going to start from the location 0, 0. So we're going to start with zeros on both x1, x2. Okay. I'm also going to give you all of the parameters. So let's say that our initial step size. So let's start with a step size of 1.0. Okay. So let's go with the minimum step size of 0.05. So once the step size kind of falls below that, then we're going to stop the algorithm. Okay. Okay. And then the number of iterations, let's set that equal to 500. Okay. All right. And so this code is posted on Canvas. And so, for this next section, where I'm going to show you the code, you can take notes, but don't write down the code in your notes. The code is actually available for you online. Okay. So the code is u underscore NLP underscore example 2. Okay. All right. So if you wanted to look at this code again on. All right. Any questions on this before we jump into code? Oh yeah, for sure. Yeah. Okay. All right. So let me go ahead and switch to the computer here, and I should have opened MATLAB. I do this at least once per week. Thursday, I'll remember to open up MATLAB before, but next Tuesday, probably not. Okay, and I'm pretty sure I downloaded the code too. Let me just check and see. Oh, I need to download the code too. Okay, so you'll get to see where it is on Canvas. Duo. Okay. So I'll post all the codes within the weekly pages, but if you're not sure where to go, you can go to Files, Code Examples, and then scroll down here. Okay. So you can see we have UNLP randomwalk.f. So I'm gonna go ahead and download this code. Okay, so I'm gonna open up here. Oh, I had it open. Okay, so this is the code within MATLAB itself. So actually, let me go ahead and make this a little bit bigger just so you can see. Okay, so you can see here it's a fairly short code, so it's less than 15 lines long. But let's go through each line of code. Okay. All right. So if you look back in your notes and you'll see, how this algorithm is implemented, we're just going to go straight from the top. Okay. Okay. So our first step here is we need to define our initial guess. Okay. And so that's what this line of code here does. And so what we're saying is that x1 underscore 0 and x2 underscore 0 are both set to 0 because we are setting our initial guess to 0. Okay. Next, we need to define all the other parameters of our algorithm here. We have n. So n here defines the maximum number of iterations per cycle. And so we're setting that equal to 500, just like the example said. We have our initial step length, and so our step length here is set to 1.0, and our minimum step length is 0.05. Okay. Okay, so this line, this line, this line, and this line are all part of part 1 of the algorithm. Okay. So step 2 of the algorithm is to evaluate the objective function at the initial point. Okay. Oh, question in the chat, sorry. All right, question. So how does random walk account for local minima and maxima? Could it get stuck when comparing new step to old step when at a local extrema value? That's a great question. So the short answer to your question is that it by itself it doesn't. And so random walk is one of those algorithms that could get stuck in a local extrema. And so the thing is especially with multi-dimensional problems, especially once you get into higher dimensions like 3, 4, 5D, is that there are a lot of, I call them pitfalls, where, the algorithm may think that it's finding an optimum, but it may not be the best optimum. And when you have random walk, where you're just kind of randomly stepping in a direction close to your current one, if you get stuck in a local minimum, you're just kind of stuck there forever. Now there are ways around this, and so the way that people usually get around this is by modifying the algorithm a little bit. So one simple thing that you can do is that, maybe after you reduce your step size to a certain point, maybe you restart the algorithm and then you try making the step length really large. So you kind of reset the algorithm with a large step length and see if there's anywhere that's kind of further away that needs an improvement. And if so, then you can kind of jump to that location and then restart your algorithm from there. So that's one way to kind of force the algorithm to kind of jump out of a local minimum. Another way to kind of avoid that problem is to choose a better starting point. Okay. So remember I mentioned before that choose your starting point here is actually probably the most important thing for your algorithm. But the problem is when you're doing this on a fresh problem, you probably don't know exactly where to start. So what you can do, and in fact a lot of people did this for their final project last year as well, is that they combine random walk together with a Monte Carlo method. So remember, Monte Carlo method doesn't have that restriction of getting stuck. In fact, it just kind of jumps all over the place, which is kind of its greatest strength. And so maybe you start this with the Monte Carlo, you kind of you find a place that's pretty close to the optimum, and then you use random walk to kind of get you as close to the optimum or refine your point as much as possible. Yeah, no, those are good thoughts, and I'm glad you're having those thoughts, because there's every algorithm that we're going to talk about has its weaknesses. There's no perfect algorithm that's going to work for everything. If there was, I'd only teach that algorithm. There's no point in going over everything else. But the reason there are so many algorithms that there are weaknesses, and the weakness of random walk is exactly as you described, where you can kind of get stuck in a particular area. Okay. All right, so coming back to the algorithm here. So after we've, so far we've defined our initial point, we've defined all of our parameters here, and we've evaluated the objective function at that initial point. Okay, so all that's good. Next, we start to take random steps. Okay. All right, so you can see here we actually have a nested for loop in here. So we have one for loop that's kind of like one while loop that's kind of like the master while loop for the entire algorithm. Okay, and so while our step length is above our minimum step length, as long as we haven't reduced the step length enough, we're gonna keep taking steps. Okay, and then once we're inside, we're gonna start kind of the inner loop. Okay, and so the inner loop, remember the way the inner loop works is that we're gonna take a fixed amount of random steps from our current location until we have to reduce the step size. Okay. So we have a for loop from j is equal to 1 to big N, and big N was that variable that we defined earlier. Okay. All right. So next thing we have to do is we have to compute our random direction. So you can see here that we're using the random number generator within MATLAB itself. Okay. And so, just to kind of refresh your memory, whenever you type rand in MATLAB, rand is really interesting because normally for MATLAB stuff, if it's a special keyword, it highlights blue. But rand actually doesn't highlight blue, but it's still a special kind of keyword there. Okay. And so what rand is going to do is that rand generates a random variable or random number between 0 and 1. Okay. So it generates some decimal between 0 and 1 and returns that there. Okay. But, for our random directions here, we need to generate a random variable between -1 and 1. Okay. So we have to modify our random number generation a little bit. Okay. And so what we can say is that R1 is equal to -1 plus 2 times rand. Okay. And so if you remember from when we went over Monte Carlo methods last Thursday, this is the general formula that we use to generate a random variable where this is the lower bound. This number right here, this 2, that is the range. And so that's the difference between the upper bound and the lower bound. And then we multiply that by the random variable. Okay. We generate R1, R2. Okay. We compute the magnitude of that direction. Okay. Okay, and so the next thing that we have to check here, and so this part actually is optional, and that's why I kind of didn't go over it in the notes. One thing that you can check is that you can check to see if your random magnitude is actually less than 1. And so this is kind of just like a sanity check to make sure that you didn't just end up with zeros on everything, or you just end up with a very small direction. So this checks for what's called biases. It's somewhat kind of optional because the way that we're running this algorithm, we're running it with so many iterations. Even if you do have a little bit of bias, it's not that big a deal. But that's kind of what this does here. But we can easily just kind of cancel this out, and so I can just kind of comment that out and comment that out, and the algorithm will work just fine. Okay. Okay. So once we compute the magnitude, we're going to take a step. And so this is probably the most important part of the algorithm right here, where we're taking a step. And so we're computing a new value for x1, a new value for x2, where it's the old value for x1 plus the step length multiplied by the direction divided by the magnitude. Okay. And then we're going to compute the objective function at this new location here. Okay. All right. And so now here we check. And so I don't know why I don't have a comment here. We're going to check to see if this new location improved the objective function. Okay. And so if this random step improved the objective function, then we're going to check to see if f trial, this is the objective function evaluated at our new trial point. If that's less than f best, then we moved it. Okay. So we reset the values for x1 best and x2 best, and we set the f best to there as well. Okay. All right, and so this repeats. This is a for loop, so it repeats a set number of times. And then once we kind of reach the end of that for loop, we then reduce the step size before returning to the top of the while loop. Okay. And so you can see here that I'm taking a fairly aggressive approach here. So I'm taking the step size and reducing it by a factor of 2. Another way that you can do this is that maybe you reduce the step size. Maybe you only reduce it by 20%, and so you multiply by 0.8. And so that'll be, it'll slow down your algorithm because it'll take time for your step size to decay. But it'll probably lead to it'll be a bit more reliable in finding out. Okay. Okay. All right. Any questions on this code here? Okay. All right. So once again, this code is available to you online. So definitely take a look at this code and definitely use this code when you're doing your homework. Questions?
Yeah, it will run iterations from 1 to 500, or is there a way where it finds the optimum and it's like that?
Yeah, that's a good question. So it'll always run that 500 iterations.
How does it know if it goes like beyond optimal? Oh, because it goes back.
Exactly. Yeah. And so if it just happens to land at the most optimal pace, then it'll just always stay there. So no matter what direction that you step in, it's just never going to move it because it's never going to find an improvement on the objective function. Yeah. Ideally, you bring up a good point though, where ideally if you do find a really good spot, then you just want to stay there. You just don't you don't want to bother doing all this other checking because it's just a waste of time. So that's kind of another weakness of this algorithm, is that it doesn't really know once it reaches kind of the peak optimum value.
And how many times will it reduce the step length?
Yeah, it depends on how quickly you reduce it, and then it depends on your minimum step length as well. So in this case, our minimum step length is 0.05. So let's see, and then we're halving it. That's what it was in kind of the default. And so if we start with a step length of 1, then after this first iteration, it's going to be a step length of 1/2. Then it's going to be 0.25, then 0.125, and then 0.0625, and then 0.03125. And so how many reductions was that? 1, 2, 3, 4, 5. 5 reductions.
So when you were defining the algorithm, you were saying that it needs to stop when the step length becomes too small.
Mm-hmm.
So what does that mean? Well, how do you define too small?
Yeah, no, that's a good question. That's kind of up to you in terms of what you expect for the problem. So there will be some problems where in this problem it's kind of like a made-up math problem. And so we can say that a step size of like 0.05 is small enough. But maybe you're optimizing the dimensions of like an airplane, right? And so in that case, maybe too small would be something less than 10 millimeters, something like that. So it's really kind of problem dependent. And so basically you set that minimum step length where you say, if we take a step length of less than this, it's not really going to change our results much at all.
Is the X1 and X2, is that usually defined as like the measurement of a distance? So if you're doing a airplane wing.
Mm-hmm. Yep. Mm-hmm. Yep. That's whatever your design variables in your problem are. So for our problems, that's most of what you're going to be designing for is kind of the optimal dimensions. Mm-hmm. And so those would be lengths of some kind. But you can also design things where maybe you're choosing a material. So maybe you're optimizing over the Young's modulus and the density, things like that too. It actually starts to get really interesting, if you have problems with design variables that are different dimensions. So maybe you're optimizing the lengths of your part, but also optimizing the material properties. And so that actually kind of adds an additional wrinkle that we'll probably talk about near the end of the semester, because it's kind of relevant to your final project. All right. Any other questions on this code here? Oh yeah, that's a good point. Okay, so you can see it runs pretty fast just because this objective function is pretty cheap. And so what is our optimal point here? So our optimal point, let's see, x1 best. So x1 best ended up being about -1, and then x2 best ended up being about 1.5. So actually, if you kind of remember this objective function here, this is the exact same objective function that we were working with Monte Carlo. So you can see here the optimums are not as close as it was in Monte Carlo, just because we can probably reduce the step length a bit more, but we get pretty close. And so this algorithm succeeded in finding the optimal location. Okay. And the benefit here is that it did so with far less iterations than Monte Carlo, because I think the Monte Carlo one we ran it for like 90 million iterations or just something ridiculous like that. So this one we only ran it by, let's see, 500 times 5, so only 2,500 iterations. So it was much more efficient in terms of that. Okay, cool. All right, so let me go ahead and bring back the iPad. Okay, So before we move on to the next algorithm, what I wanted to show you is, what this algorithm would look like in pseudocode. Okay. Okay. So, the reason I want to show you the pseudocode is that it's a great way to kind of practice coding, without actually having to open up math. Okay. It's also kind of going to be the way that I test you guys this on the midterm, just because I can't have you guys write MATLAB code on the midterm itself. And so, but I do want to be able to kind of test to see if you understand the logic in terms of how these algorithms are implemented in a computer code. Okay. So the cool thing about pseudocode is that it's not specific to any particular language. If you want to be kind of pedantic, pseudocode is written in the human language. So it's meant to be kind of human interpretable statements that show how a code is implemented. So you try to keep it as kind of one-to-one in terms of each line of code that you would write would have one line of pseudocode, but you write it in a way that that a human can understand. All right, so I'll just do kind of a very quick pseudocode implementation of the previous example that we did. Okay. Okay. So this is the pseudocode implementation of random walk. And so let's see. So usually pseudocode is written in bullet points. And so each bullet point kind of represents a line of code. Okay. Okay, so the first thing that we do here is we need to set our initial design point. And so we're going to set x1 not equal to 0.0 and x2 not equal to 0.0. Okay. Next, we need to define initial step length. Okay. Remember that was another line of code in the code that we just ran. Okay. All right. Next, we need to define max iterations. Okay. And then finally, we define the minimum step length. And so that's the smallest step size that we'll tolerate before we terminate the algorithm. And so we set that to 0.05. Okay. All right, so what you can see here is that, the pseudocode is kind of like a one-to-one kind of interpretation or one-to-one kind of transcription of our code. It's just kind of written with, some additional notes to kind of explain each step. But, each line here represents one line of our code. Okay. Okay. So the next line that we did was we computed our initial objective function. Okay. And whenever you can put in formulas here, that's always helpful. And so for our initial objective function, we have x1 naught minus x2 naught plus 2x1 naught squared plus 2x1 naught x2 naught plus x2 naught squared. Okay. So that was the first steps of our algorithm, right? So that was all kind of the initial steps. Okay. All right. So now we get into the loops. Okay. So whenever you have a loop in your code, right? A loop means that you want to repeat code, right? And so in your pseudocode, the way that you can express that is you can say repeat. Okay. And our first loop that we went over in our code was a while loop. So we're going to repeat while step length is greater than minimum step length. Okay. And then right underneath that while loop is another repeat statement. Okay. So we're going to repeat. Okay. And if you look back at the code that we just went through, we had another for loop right underneath that while loop. And so we're going to repeat for n is equal to 500 iterations. Okay. Right. And then under there, we have, we computed our random directions, okay, R1, R2. Okay. And then kind of so on and so forth. Okay. So you can see here that, the pseudocode, pseudocode tries to be as faithful as kind of one-to-one to the code as possible. You don't have to mimic every single line of code. And so, when you get the exam, you're probably going to see, one of the problems maybe, give me the pseudocode for random walk, right? Or it'll say, write me a pseudocode for random walk. You don't have to get every single step here exactly in the right order, okay? That's not the point of pseudocode. The point of pseudocode is not to, it's not to test your memorization to see, do you remember every single step? The whole point of the pseudocode is just for me to kind of, glean, first of all, do you understand this algorithm in terms of, the logical steps in which it needs to take to get to an optimal solution? Okay. So that's very clear, if you can write down an algorithm in pseudocode. And number two, do you understand, just a little bit of kind of the logistics or the details in terms of how to get this algorithm into a form that the computer can understand logically, with some keywords here, like defining variables, okay? Or repeat, okay? And then, for an if statement, for an if statement in your code, you'll kind of express that in pseudocode as, check if, okay? Because an if statement is essentially just a check, okay? So that's what I'm looking for the pseudocode is, do you understand, first of all, do you understand the algorithm? And two, do you understand kind of at least from a high level point of view, what are some of the big steps that you need to do to implement this in code, okay? Because you'll see is that, if you read the pseudocode and you compare that to the algorithm that we kind of wrote out up here, of course it's the same algorithm. So, there's a lot of similarities, but they're not exactly the same because the computer has to, do things in a certain way, in a certain order with a certain steps, in order for it to, execute. Okay. So the pseudocode is, basically putting the logic of an algorithm into a computer digestible format, okay, without having to worry about all the syntax that you would normally have to do. Okay. All right. Any questions on that? Okay. We'll do more examples of pseudocode, for the other algorithms, for the next two that we're going to go over. I'll introduce the next algorithm today, but we'll probably finish it up on Thursday. Pattern search and or coordinate search and pattern search are kind of really good ones to know for pseudocode. Okay, so for the last 5 minutes today, I want to kind of introduce the next algorithm. So the next algorithm that we're going to go over is called coordinate search. Okay. So the idea with coordinate search is actually very similar to random walk. Okay. And so in coordinate search, again, you're going to start from an initial point, and then you're going to optimize the function by taking steps from that initial point. Okay. So just like random walk, coordinate search, you're going to start with an initial point, and you're going to take steps away from that initial point to improve your objective function. Okay. The difference here is that coordinate search is not going to rely on randomness at all. Okay. So randomness, randomness is very interesting when you're talking about kind of a computational algorithm. Randomness can be very powerful, but it can also be very random, right? So its greatest strength is also its greatest weakness. So, sometimes when you're doing an optimization problem, it's very obvious kind of which direction that you should be stepping in. But if you're relying on randomness, you're kind of waiting to see that until the random direction kind of hits on that direction. Okay. So coordinate search kind of aims to take the randomness out. And so instead of stepping in random directions, instead, coordinate search takes the following approach where, when you have a multi-dimensional problem, it's really hard when you're considering all dimensions at the same time. Right? So if you have a 3-dimensional problem, 3 design variables, and you're changing all 3 at the same time, it's hard to do so in a way that's going to reliably improve your objective function. That's why we do randomness. Okay. Coordinate search tries to simplify this. So instead of stepping in random directions, coordinate search is only going to step in one direction at a given time. Okay. And so in other words, coordinate search only aims to change one design variable at a time. Okay. And so if I were to draw it out, it actually kind of looks like a really interesting pattern. Okay. And so if I draw our usual 2D design space here, x1, x2, if you were to optimize this with coordinate search, you would basically just move in directions that are parallel to the coordinate axis. So you maybe move this direction, you move this direction, and this direction, this direction, this direction, this direction, this direction. Okay. And so with this pattern here, you're basically only changing either x1 or x2 at a time, and you're leaving the other one constant. Okay. And so what's the benefit of this? So the benefit of this is that by changing only one variable at a time, each time that you take a step, you essentially have a one-dimensional optimization problem because you're holding everything else constant. And, you know, if there's one thing that we're really good at this point, because we've covered it for a long time, is one-dimensional optimization problems. So basically, every time you take a step, you can basically solve a miniature one-dimensional optimization problem, you know, before moving on to the next step. Okay. All right, so that's kind of the logic. And so when we come back on Thursday, we'll talk about kind of more specifics of the algorithm, how it's implemented, and we'll go over its MATLAB implementation and pseudocode implementation as well. Okay. All right, any questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today. So thank you guys for coming. Hope you guys have a good rest of your day, and I will see you on Thursday.